Let's look at a situation where we have a more complex circuit, where I've got different branches. Now, if I just had a case where I had where I could isolate it, so I had a whole bunch of resistors together, you might think, wait, did we not do something like this for capacitors? Could we do something like this for resistors? The answer is yes. But I'm going to start actually with a more complicated circuit where I've got a battery in there, so there's no way I can just break this down. Well, the advantage is that if I have n unknowns, I need n number of equations to solve those unknowns. I can get a lot of equations right here. For example, I can use the conservation of current, and let's see, so places like nodes where wires go in and go out, I can use the conservation of current. Okay, so what I need to do first is I need to define the direction of currents. First, I need to define one current per branch. For example, the current passing through resistor D has to be the same as the current passing through battery 1 has to be the same as the current passing through resistor A because of the conservation of current. The current in this side of resistor D has to be equal to the current out this side of resistor D, and there's no way for that current to change before it interacts with battery E1. It's got to be the same coming out as it was going in, and there's nowhere for that to change until it goes through resistor A. It's got to be the same out as it was coming in. Then we hit this node and things can change. So I need to define one current per branch. Now, I'm going to need to give those currents a direction. What if I'm wrong? Who cares? If I'm wrong, at the end of the day, I'll get a negative number. So I'm just going to call this, let's see, I've got 1 and 2 and A, B, C, and D. I'll call this current alpha, current beta, and current gamma. If I guess their direction wrong, or incorrectly, then all that means is that I'll get a negative sign at some point where I solve for some things, so that I can say, okay, look at this node. The current in is current I alpha plus I gamma, and that has to equal the current out, I beta. At this node, the current in is current beta, and the currents out are currents alpha plus current gamma. Unfortunately, these two equations are exactly the same. At the very least, though, I've got a thing that I can use. So, I get one equation out of these nodes that current alpha plus current gamma is equal to current beta. Now, suppose I just hook up all of these pieces and go to it. Well, in that case, then then I might not start off knowing what those three currents are. So suppose I'm solving for those three currents, I would have three unknowns, one equation. I am not done yet. Well, I would use this for a closed loop. Now, if I look at this arrangement, let me draw that arrangement down here. I have three different loops. The loop on the left the loop on the right. And the loop on the outside. So, in order to use this realization that over a closed loop the change in potential is 0, I must pass those loops, one on each side. Now, which direction should I go? Should I go clockwise or should I go counterclockwise? It does not matter. They'll be exactly the same equation, except everything's multiplied by -1. So, just for grins, let's go clockwise on each loop. Clockwise on the red loop, I need to pick a place to start. Let's start here. Okay, I go from the negative to the positive on battery number 1. So the voltage increases by E1. I'm going with the current over the resistor, so the potential should drop. And it should drop well, from Ohm's law, delta V, the change in potential, should be equal to the current times the resistance. Okay, here I've defined current gamma as going into this node, so I'm going against the current. So the potential should increase I gamma times resistance C. I'm going from negative to positive. So the EMF, the voltage will go up by the EMF of the battery 2. Passing around, I'm going with the current. So the potential will drop by I alpha times RD, and then I'm back where I started with, so hey, that equals 0. Now, okay, let's look at the blue loop. Start from the same place. I have the current goes up by E1. The potential goes up by epsilon 1, by E1, the EMF of battery 1. The potential drops by I alpha times RA over resistor A. I'm going with current beta, so the potential drops I beta RB. And I'm going with the current, so the potential drops I alpha RD. And I'm back where I started from, so that's 0. Now, take the green one. I need to pick a place. I'll pick here. And I'll mark saying that I picked here for the second one. Okay. Still going clockwise. I'm going against this current this time, so the potential goes up. So I have current beta times resistor B. I'm going against the current yet again, so I've got current gamma times RC. I'm going from negative to positive on the battery number 2, so the potential goes up, E2, and that equals 0. So, for this system, I have 4 equations. So as long as I have 4 or fewer unknowns, I'm entirely good to go. I'm going to test out, I don't want to just grab numbers off the top of my head, but I want to test some sample, I'll put up some sample numbers for some sample cases here. Then I'll tell you, here are my results, and I'll show you a way to check them using one of the physics simulators. That should be quite helpful, I hope.